These stars would be the universe's very first stars, consuming at searing temperatures from unadulterated hydrogen and helium, originating before the making of heavier elements by stars later on through nuclear fusion. These types of blazing, primordial stars are mysteriously gone in the nearby universe, implying that they no longer exist, and we can perceive them from light that is billions of years old. They're extraordinary. The farthest source appears very compact, with colors suggesting it holds a stellar population generally without heavy elements, perhaps even containing population 3 stars. However, only Webb spectra will provide definitive answers. Distance estimates for these two universes depend on measuring their infrared variations. In the future, spectroscopy measurements showing how light stretches in the expanding universe will independently confirm these cosmic measurements. While we wait for these estimates, the JWST has been discovering even more fascinating things: dark stars. The JWST isn't just finding ancient galaxies, it's finding new and wondrous things every day. Scientists are astounded by the astonishing discoveries they're making through this device. One of these discoveries occurred in August of 2023. During this period, scientists believe they found something called dark stars. Dark stars were first hypothesized in 2007, and some scientists aren't even certain these stars actually exist. Dark stars aren't powered by nuclear fusion but by the self-annihilation of dark matter. Dark matter is an invisible substance comprising 85% of the universe's matter. These candidate dark stars, while requiring further confirmation, could potentially reshape our understanding of early star formation. Despite being called dark stars, they're not the exact opposite of the giant balls of plasma we know. Surprisingly, dark stars could have emitted a luminosity 1 billion times greater than the Sun and reached a mass 1,000 times larger. Although never definitively observed, simulations suggest that they may have formed shortly after the Big Bang, originating from clouds of pure hydrogen and helium collapsing within protogalaxies rich in dark matter. In a report published in the Proceedings of the National Academy of Sciences USA, researchers suggest that at least 3 distant objects previously identified as galaxies by JWST may actually be single, extremely massive dark stars. These galaxies were part of the JWST's Advanced Deep Extragalactic Survey, also known as JADES. The objects in question were GSZ-13, GSZ-12, and GSZ-111. The discovery, if confirmed, would be groundbreaking. According to the co-author of the study, it can't yet be proven that these objects are dark stars, but their characteristics align with both dark stars and galaxies hosting fusion-powered stars. The technology of the JWST holds the potential to resolve this uncertainty, with more observation time being the key requirement. Another co-author anticipates the hope of finding one such dark star during JWST's operational lifetime. The origin of the universe's first stars presents 2 possible outcomes. The prevailing belief is that these early stars were powered by nuclear fusion, much like modern stars. However, they would have been nearly devoid of heavy elements beyond helium, since such elements hadn't yet formed in the early universe. These are the same as the population 3 stars we mentioned earlier. But there's another intriguing hypothesis. In 2008, researcher F and her colleagues proposed an enthralling idea that the universe's earliest stars could have drawn their energy from dark matter. This mysterious substance, which interacts solely through gravity, remains largely unknown in composition. In the early universe, dark stars may have emerged from collapsing clouds of helium and hydrogen formed during the Big Bang. Many theories suggest that dark matter particles have the unique quality of being their own antiparticles. Antiparticles have the same mass but the opposite electric or magnetic properties of their given particle. For example, the antimatter particle of an electron is a positron, which has the same mass as an electron but the exact opposite charge. When these two collide, they annihilate each other. If dark matter particles are their own antiparticles, their collisions would result in self-annihilations and particle decay. These interactions within the collapsing clouds could have initiated a series of particle interactions, resulting in the production of photons, electron-positron pairs, and neutrinos. Most of these particles would have remained within the cloud, but neutrinos would have escaped, as they barely interact with matter. The other particles would have transferred their energy to the hydrogen and helium, heating the cloud and sustaining star formation and growth. These stars would have taken shape at the centers of mini-halos, which are early protogalaxies emerging around 200 million years post-Big Bang, before the presence of elements heavier than helium and hydrogen. These small halos were primarily composed of dark matter, creating ideal conditions for fueling the birth of these dark stars. This dense concentration of dark matter existed only in the early universe, meaning dark stars could only form in this time frame. These stars, unlike their nuclear-fueled counterparts, remained relatively cool. What's more, they didn't transmit the high-energy photons commonly connected with stars. This quirk permitted them to constantly aggregate mass, making them expand altogether throughout their lifespans. These stars are fairly paradoxical. They look like the sun in terms of surface temperature, however, they shine with a brightness a billion times greater, reviving a whole world filled with fusion-powered stars. This hypothesis perfectly explains another mystery researchers have trouble answering. As these gigantic dark stars reached the end of their life cycles, they would have collapsed into enormous black holes. This could also explain the presence of some ancient, very massive black holes observed in the universe, which appear too large to have formed quickly from population 3 stars powered by fusion. To search out these dim stars, the researchers combed over the JWST catalog of objects, tracing back to the early universe almost 14 billion years ago. Among the limited data on electromagnetic emissions from these objects, only 9 were considered viable candidates. 3 of these closely resembled the characteristics of dim stars. They displayed a high redshift, indicating aged and distant origins, and they seemed to originate from a single source, like a star, rather than a diffuse galaxy. The scientists currently have only limited observations of these objects, preventing further detailed analysis. A definitive marker of a dim star's presence would be a specific feature in the electromagnetic spectrum, where light is absorbed by a particular helium isotope unique to dim stars and absent in galaxy spectra. Identifying this marker would require extended observation, a process deemed unfeasible due to the JWST's high demand for numerous astronomical investigations. However, preliminary findings suggest that if these objects were indeed dim stars, 2 would have a mass about 1 million times that of the Sun, while the third would measure roughly 100 times the Sun's mass. The research team is currently working on an automated approach to identify additional dark star candidates, some of which may require less observation time for confirmation. They expect to find many more potential candidates. If they directly observed a dim star, it would be a groundbreaking achievement. Nevertheless, alternative methods exist for detecting dim stars, including examining their signatures within the cosmic microwave background, CMB, a faint radiation glow remaining from the universe's hot initial stage. Observing a dim star wouldn't just reveal new insights into the universe's early formation but would also offer a unique opportunity to directly study interactions involving dark matter particles. Observing such interactions would significantly enhance our understanding of dark matter's nature as a particle. While the concept of the dim star doesn't alter much of what is currently established in cosmology, some researchers have argued that we might be wrong about the age of our universe. The estimated age of our universe could be incorrect. When we said that the JWST is changing our understanding of the universe, we weren't exaggerating. We are finding things that are disconnected from our current scientific understanding of the universe. We know that the JWST detected highly evolved galaxies only 325 million years after the Big Bang, yet these galaxies have incited intense speculation among cosmologists. One cosmologist is saying that the universe may be twice as old as we thought it was. Current scientific consensus places the Big Bang at 13.8 billion years ago, but Professor Rajendra Gupta proposes a revision. He suggests that it's actually 26.7 billion years. Anyway, another cosmologist utilized the Sagan standard, saying that phenomenal claims require phenomenal evidence. So, did Gupta have adequate proof to support his case? To comprehend his hypothesis, we first need to understand how cosmologists arrived at these numbers. Determining the age of celestial bodies, let alone the universe, is no simple feat. This assessment relies on observations of the cosmic microwave background, CMB, radiation and measurements related to the universe's expansion. The CMB reaches back only 300,000 years after the universe's birth. It spread across the universe and constitutes the earliest recognizable radiation. By meticulously examining temperature variations within the CMB, cosmologists inferred the universe's age. Hubble's law, established by astronomer Edwin Hubble during the 1920s, further contributes to this. It establishes the association between galaxies' distances and speeds, aiding in determining the rate at which the universe expands, known as the Hubble constant. By tracing this expansion backward, we can estimate the time of the Big Bang. Interestingly, Gupta's model embraces a different perspective. It draws upon the tired light theory, initially proposed by physicist Fritz Zwicky in 1929. Gupta uses it to explain the redshifting of photons coming from distant galaxies. Now, recall that redshift arises from the stretching of photons due to the universe's expansion. The tired light theory suggests that photons gradually lose energy as they travel. While this contradicts current observations, Gupta suggests that by allowing this theory to coexist with the expanding universe, the redshift phenomenon could be reinterpreted as a hybrid phenomenon, not solely due to expansion. The presence of galaxies in the universe's mid-million years is often called the impossible early galaxy problem. Scientists have trouble explaining why these ancient galaxies formed so early. Estimating the universe's age faces challenges from physics and observation. Our current knowledge suggests galaxies require time to evolve, accumulating stars and structures through various processes. However, advanced telescopes like the JWST have revealed mature galaxies during the universe's youth, challenging our understanding of cosmic development and evolution over time. Gupta essentially suggests that the universe could be much older than it actually is. To resolve this impossible galaxy issue, Gupta also introduces new variables that change over time. This shifts the birth of early galaxies from 100 million years to several billion years, leading him to conclude that the universe might be around 28 billion years old. Scientists are not accepting this hypothesis, though. They say that a simpler explanation could be that we don't yet fully grasp how galaxies developed in the early universe. Some even believe the impossible galaxy issue is an exaggeration. Researchers agree that there are indeed unanswered questions about early galaxy formation in JWST observations, but nothing is inherently impossible. Experts don't foresee Gupta's hypothesis revolutionizing cosmology anytime soon. Our current understanding of the Big Bang and the universe's expansion is grounded in abundant observational evidence and has successfully explained various cosmological phenomena. For Gupta's research to gain traction, it would likely need further examination and theoretical development. The standard model of cosmology asserts the Big Bang occurred around 13.8 billion years ago. This is based on measurements from various sources, including supernova data, galaxy distribution, and observations of the universe's expansion. Gupta's paper primarily considers supernova data, which scientists regard as insufficient. Thorough testing in various ways is essential. Gupta's theory has garnered significant media attention, but researchers attribute this to unreliable hype and question the scientific basis of the paper itself. For any alternative explanation to the Big Bang, it must account for fundamental cosmological observations. Solving one puzzle doesn't hold much weight if it can't explain established data. But what do you think? Could Gupta be justified once more research is done, or is this another theory that will lose traction as time goes on? Let us know in the comments below, and leave a like for more.